Is everybody ready to hear a little bit about the James Webb Telescope? I have a few HASP announcements here first. My name is Bill Wells with the Science, Medicine, and Technology Subcommittee, and I will be presenting today's speaker. First of all, please take out your cell phones. Make sure they are silenced. Thank you. Also, welcome to the crowd joining via Zoom in the HASP virtual classroom. Special thanks to our course technicians, Jenna Teeter and Dave Magin, for supporting the hybrid modality. If you have any questions or comments to pose at the appropriate times, we kindly ask you to wait for the microphone so that all participants, especially those on Zoom, can hear the question. Sometimes the speaker will remember to repeat the question. Other times they're thinking about their answer and don't do that. So make every effort to wait for the microphone before you speak. We look forward to welcome you to the monthly program on Tuesday, December 5th at 9:30 at Jack Miller Center for the Arts. The program is a collaboration with Holland Symphony Orchestra and will feature a live performance of traditional African music. Coffee, cookies, and conversation will begin at 9 a.m. and the program starts at 9:30. I'm sure that all of you have probably seen at least every other day in the news some new photograph from the James Webb Telescope. And it's been an evolution since the first light, is the phrase that's often used for a new telescope. Since the first light, it's been an evolution of spectacular photographs. And we have a presenter here that is going to do a wonderful job of telling us about the telescope, and I'm sure showing us some fabulous photographs. Dr. Peter Gonthier, he joined Hope College's Department of Physics in 1983. He's a member of the Astronomical Society's High Energy Astrophysics Division. He has expertise in radio, X-ray, gamma ray astrophysics, neutron stars, and pulsars. So Dr. Gonthier has a BA in chemistry and a PhD in nuclear chemistry, both from Texas A&M University. So I'll let him take it from here.
Thank you very much, Bill, and it's good to see you all. It's a privilege to be here once again. I am honored by this. I always enjoy it so much to share with you some of the great things that have been happening in the stars. My PhD was in nuclear chemistry, and so I did nuclear physics experiments when I came to Hope. Heavy ion accelerator experiments in various parts of the world. And then I had a sabbatical in Germany. We went to Germany in 1990, and they asked me to teach at the University of Gießen, which is near Frankfurt. And so I taught a course in cosmology, and I had to learn some general relativity on my own. And the second semester, I co-taught a course on compact objects, dealing with white dwarfs, neutron stars, and black holes. And then I got back, I learned about pulsars and felt very curious about them and said, gee, we know so much about them, I would like to study them. And so I came back to Hope, and NASA invited Hope College to learn about the NASA JOBE program in 1991. And so I went down to Marshall in Alabama at their NASA center and learned about the JOBE program and wrote a proposal and got funded for it for 3 years. So I figured this was my opportunity to swap horses in midstream. and go into theoretical astrophysics. So I had to do a lot of learning. It was a new field. It felt like being a graduate student all over again, and nobody knew me and I didn't know anybody. And so I continued in that. And I had to identify a NASA mentor, and I wound up identifying Alice Harding at Goddard Space Flight Center near DC. And so I wound up spending the summer of 1992 out there. In the summer of 1993, then I started taking students out there with me every summer since then, till the pandemic came. So it was a beautiful experience for the students and for me as well, as we got a place to sit in an office and study and listen to talks of other scientists. And one of the things that we saw come together was the James Webb Space Telescope that was being put together there at Goddard. And this is the Space Telescope in the largest clean room in the world. And I would get a friend to give us a tour, and we would go around the facilities with my students, and see what NASA was up to in various fields. The testing that was done, one of the things that happens is when you send something up in a rocket, it's going to shake like crazy. And then you get out into space and it's going to be cold, hot, and so all that has to be tested. And unfortunately, they shook the James Webb Telescope once it was all put together. And they came back and looked at it and found a few washers and bolts. And they scratched their head and wondered, where did they come from? So they had to take it all apart and figure out where these things came from and why did they fall out. So it was interesting. Here we see the mirrors in these different segments. This is the large mirror that reflects the light onto a secondary mirror, which is here, and then that reflects into the set of experiments that are different detectors that are done in there. So there's all these things in front of the telescope that will cause some diffraction patterns that are unique to Webb. For the last 3 summers that we went out there before the pandemic, we were able to sit in the office of John Matter. And John Matter is a Nobel Prize guy. He's the only Nobel Prize guy at Goddard. He shared the Nobel Prize with Schmoot for the cosmic microwave background fluctuations that were detected by the COBE cosmic background explorer in the early 90s that discovered these fluctuations. And then he was the senior project scientist of the James Webb Space Telescope. And we were allowed to sit in his office. So the first thing I would do is sit there in his chair, rub my hands over his keyboard and see if I could soak up some molecules of him. And here are 3 of my students in 2018. We spent a month out there, and it was just a wonderful experience for them, for myself too. John Matter was the senior project scientist up until this summer, when he retired. And now is emeritus, I guess, like myself and a lot of us here. So the James Webb Space Telescope, are we going to dim the lights by chance? Or I think we have pretty pictures, so. I guess these are dimmable to some extent, aren't they?
They are.
Yeah. Okay, thank you. The James Webb Space Telescope was launched in Christmas Day of 2021 from an Ariane 5 rocket that was launched from French Guiana, which is off the South America. And the location that it was going to be in was going to be about 1.5 million kilometers from the Earth, behind the Earth from the sun, orbiting a location that is called the second Lagrangian point. There are these different Lagrangian points, which are stable locations, and you can orbit these. And so it took some time to get out there and orbit. And then, you know, this whole thing orbits the sun. So there's a few other satellites out there like Gaia, and there is also Euclid that has recently been launched by the European Space Agency, that it too is also releasing some amazing images, and it is going to study the dark matter and dark energy and hopefully illuminate those for us in the future. So that's where it's at. It took a month or so to get out there. And then there had to be a lot of testing of equipment and focusing all the different segments of the mirror. And finally, in the summer of 2022, it was releasing its images. And this was one of them. And this is the Carina Nebula, which is in the constellation of Carina in the southern hemisphere. It's close to this large star called Eta Carina that is a very massive star and being studied significantly. Hubble has taken some amazing images of it. And here, James Webb Space Telescope is an infrared telescope. So it basically can see through clouds and be able to see all these stars that are behind this cloud of dust and gas. And you see this diffraction pattern, these spikes that the stars have. There are 6 of them or maybe 8 of them, depending on the star and how bright it is. And Hubble shows only a diffraction pattern of 4 spikes. So that's how you can tell whether the image is a James Webb or a Hubble image. This is Stephan's Quintet. It's in the constellation of Pegasus. This is a constellation that we can see. And there's 5 galaxies here. This one is NGC 7320. That's its telephone number. And then going clockwise is 7319, 18A and B, these that are in close proximity and interacting. And then this other one, which is 17. This one, interestingly enough, is about 40 million light years away. And these others are 290 million light years away. The size of this image is a fifth of the moon. And the full moon is about half a degree in the sky. Your little pinky at arm's distance will block the full moon. Your little pinky is about 1 degree. So you take half a little pinky, that's the full moon, and you take a fifth, a half a pinky, or a tenth of a pinky, and that's the field of vision that you have here. We're going to zoom in on this little box here to see that there's galaxies upon galaxies, and they just continue. There's a star over here, but the rest of these, well, there's another star here. The rest of these are galaxies. So it's amazing that in such a short exposure, Webb is able to see so far. And of course, the telescope is a time machine, right? Because it takes light a finite amount of time to travel. Yes, light is fast. 300,000 kilometers per second. But we're talking very large distances. So in some cases, it takes 1 million years for light to travel from that object to get to us. So when we look at it through a telescope, we see it as it was, however long it took the light to get to us. And so all we need to do is look further and further out, and we look further and further back in time. And so at some point, we'll get to the place where we see the first stars, the first galaxies. And then we won't be able to see through the fog that is there before the cosmic microwave background came along. So there will be a limit as to how far we can see. But it's interesting how far we are able to see thanks to the technology that has come along. I want to go back because we're going to look at this galaxy. This galaxy here, 7319, has a supermassive black hole in it. And so James Webb here is looking at the supermassive black hole and is taking a spectrum. So it's dispersing the light in the infrared, and there are these different emission lines that are corresponding to different elements. So each element has its own fingerprint in the spectrum. And so it's able to tell you what is in the near the black hole, what is falling into it, you might say, and what is further on out. So this is a 24 million solar mass black hole, and its brightness is of the order of 40 billion suns. So it's an active supermassive black hole that is accreting material onto itself, emitting a jet that gives it this brightness. Here's a beautiful image of the southern ring. There is the Ring Nebula, which is in the constellation of Lyra that we can see in our night sky. But this is in Vela, which is in the southern sky again, far away. It's about 2,000 light years away. And it's a planetary nebula, meaning that this is was a massive star of the order of less than 8 solar masses. that evolved to its end. And the outer part of the star becomes unstable and is ejected and forms this planetary nebula that just continues to travel away. And the central part of the star, the core, collapses into what is called a white dwarf. And that's an object about the size of the Earth. It's white because it's hot, about 10,000 Kelvin. And the bright star here is not the white dwarf. That happens to be another star in the field. But this is a composite of various filters in the infrared that are put together to give us a nice color image. So the colors are false. They're not necessarily the way we would see it because this is in the infrared. So there's two different infrared cameras. There's the near infrared and there's the mid-infrared camera. So this is close to the infrared and this is kind of further away in the infrared. And as you compare these images, they're quite different. Still, there's many, maybe 6 different filters in each of these that they can be combined in a way to give us a color representation of the object. Now you can see 2 stars in the center here. The dim one is the white dwarf. The bright one is the one that appears here with the spikes. One of the things that the astronomers take advantage of is being able to use what is called gravitational lensing. So you have a telescope in space and you have another telescope which is produced by gravitational lensing. And this is due to the fact that you have a massive cluster of galaxies. So we're showing here a massive cluster of galaxies. So there's a certain distribution of mass or matter that works as a lens. This is a prediction of general relativity, Einstein's theory. And what is being imaged is an object that is way beyond the massive cluster. The image is enhanced, that is magnified, and also distorted. So astronomers are able to look at the distortions and see what the object is, how far away it is. And so in this way, they're taking advantage of a telescope within a telescope, you might say. And you can go back and see very early in the universe. So the universe is 13.8 billion years old, and we are getting close to that. James Webb is supposed to look at the earliest galaxies, the first galaxies, and some of the first stars that were formed in our universe. And that's amazing. That's how far technology has come. And we're able to answer further some questions, and perhaps many other questions are being raised as well.
We do have a question back here.
Okay.
James, how long do you think James Webb will take to get to viewing the end edge, the far edge? I mean, is that
well,
anticipated even?
The exposures that are being taken right now are less than a day. And there's a lot of science to be done and a lot of priorities. So looking at empty space for a long period of time is not one of them yet. And I'll show you some deep fields and compare them to what Hubble has been able to do. So this image was also released. It was released by President Biden on July 12th of 2022. This exposure took, what is it, about 0.8 days, about 14 hours or so of exposure. And there's a lot of galaxies in here, yeah? And this is the size of the image in the sky is the size of a grain of sand being held at arm's length. That's a patch of sky that is being looked at. So it is like taking an object that's 0.5 millimeter, and that's what you're looking at in the sky at this point. And it's looking at a massive cluster, SMACS 0723, which is about 4 billion light years away. That's what this G stands for, Jillian light years. So that's a billion light years. And you can see some warps, some lensing that is taking place from an object or a galaxy that is further behind there. If we zoom in a little bit closer, you can see some of the warping that is taking place. And sometimes the images appear to be different objects, but they could be the same object showing up as two different objects in the photograph. If we go back here, you can see that the light that is being lensed can travel in different paths. And so we might get an image that took this path and another image that may have taken this other path. And so we get these multiple images. And the other interesting thing is that the paths may have taken different amounts of time for the light to get to us. So you might sample the same object, but at different times. And that's the interesting nature of gravitational lensing. So that's the image of gravitational lensing here. This is a very interesting one. This is a different massive galaxy cluster, RxJ 2129, in the constellation of Aquarius. Aquarius is in our sky, kind of low in the horizon. And here we see a gravitationally lensed group of galaxies. And there are 3 different images that are gravitationally lensed. The one in the center here is showing a supernova type 1A going off in a galaxy far, far away, because this is actually in the background of this massive cluster. They could tell if they took a spectrum of this, how far away it is. But this other image here at the bottom occurred 320 days later than this image, and this occurs 1,000 days later. Now, how do they know that? Presumably, they have to model the mass that is there and be able to figure out what these different paths are. And they've gotten very sophisticated these days. And this is certainly not my field, so. But anyway, here's another image of a galaxy cluster, and it's yet another one with a different telephone number. And it's imaging a star that is 13 billion light years away. So this is a star in the very, very early universe, within, say, 800 million years of the beginning of the Big Bang, of the actual birth of our universe. And I'm blowing this little square up because it's showing this arc. And within this arc, you see these blobs, which correspond to the star that they've named Iridel. And I guess this is a character that is in Lord of the Rings, is that right? And so this is one of the earliest stars, you might say. There are other types of stars that might be further away that explode, and we can see them because of their brightness in our sky. And we've known about these for some time, and they're cosmological in nature. Okay, so I'm going to talk about how far they're able to, or how is it that they determine how far things are in the galaxy, in the universe. And for that, I need to talk a little bit about the dispersion of light. Newton was the first guy who was able to discover that you could take white light and disperse it into its colors. And this is being illustrated here by a prism dispersing it in its colors, and then selecting what part of that spectrum you want to expose or take a picture of or something. Another way of doing this is using a diffraction grating. And usually fancy astronomical spectroscopes will have a diffraction grating with many thousands of gratings per inch that will, and the more gratings, the more you can disperse the light. And so that's what's inside of the James Webb. And I would guess that there is maybe 2 of these that are dispersing the light in the infrared. So this is the visible spectrum in its colors. And the blue end or the violet end is about 400. The units of wavelength here is in nanometers. A nanometer is 10 to the minus 9 meters. And so we go from 400 to 700. The 700 is a red end. And below the 400 is the ultraviolet. And beyond the 700 is the beginning of the infrared. And that's where James Webb is looking. In some case near the infrared, near the red here, a little bit extended out. And in other cases in the mid-infrared. And so what we're going to talk about is blue shifts and red shifts. And that is, I'm mainly going to talk about a red shift, and that is that the spectral features get shifted toward the red end. And why do they get shifted? This is because of the Doppler effect, which has been known for centuries. And you've all, I'm sure, heard this, especially at a train crossing. When the train goes by, you hear the change in pitch of the whistle. This is basically a change in frequency or a change in wavelength. And if it's approaching you, the frequency increases, and therefore the wavelength decreases. So that means it gets blue shifted, okay? If the train is moving away from you, or the ambulance here, then the wavelength increases and the frequency decreases. So in this case, we say it's redshifted. So we look at the spectrum of galaxies and we see whether they're redshifted or blue shifted, meaning whether they're coming toward us or approaching us. Coming toward us or moving away from us. There we go. And how far they're shifted is basically related to the velocity. Now, for slow moving things, it's quite simple. If things are moving fast, then it gets much more complicated. Here's an example. There are 6 different spectra here. There are 2 groups of 3. The spectra here is of hydrogen. It's in the Balmer series. It's in the visible. So we're actually looking at a spectrum of the visible light coming from hydrogen. Now what's happening here is you have a source of light that is going through the hydrogen gas, and the hydrogen gas is absorbing at certain particular discrete features due to electron transitions in the atom. And these have specific wavelengths. So there's a fingerprint associated with each element. This is what you would see in the lab at rest, not moving relative to the detection or the exposure. And this is the shift if the object is moving at 3,000 kilometers per second towards you. And you see these lines are shifted toward the blue end. So we say this is a blue shift. And this is actually going faster, and the shift is larger. And here the shift is toward the red end where the object is moving away from. So next we have the very first redshift measurements of galaxies, or what are called galactic recessional velocities. They were first observed by this fellow, Vester Silfer, in 1914. And this took photographic film, and he would have to get inside the telescope where the primary mirror comes into focus. And there he had a diffraction grating, and that then exposed this film. And of course, he had to keep the telescope focused on the galaxy, and the exposure took hours on end. And so there were very difficult measurements to make. And he was the first guy that was able to see that most of the galaxies, especially the ones that are outside of our local neighborhood, because our local neighborhood is gravitationally bound, and those galaxies are approaching us. But outside, they're all moving away from us. And that's what he discovered. And then Hubble was able to measure the distance to those by looking at Cepheid variables, and a technique that was developed by Henrietta Levy around this time, that the periodicity of these Cepheid variables was proportional to their luminosity. So if I have a 100-watt light bulb and it's out there somewhere, I take a picture of it, I'm measuring the brightness of it, and I know the luminosity of it, or the absolute brightness, then the thing that relates those two is the distance squared. So it dims as the distance squared. So if you know the luminosity of an object and you take a picture of it, then you can determine the distance. So Hubble was able to determine the distance. And what they're able to see then is that the further out that you looked, the galaxies were moving faster away from us. And that was known as Hubble's law. And there is a slope that is known as the Hubble constant. So if you make a plot, okay, well, here's some actual spectra that were taken of some galaxies. This is the velocity of the galaxy in kilometers per, sorry, this is the distance. Take my glasses off, then I can read. This is the distance in light years. So this is 78 million light years away, the constellation of Virgo. And this galaxy is receding from us at 1,200 kilometers a second. And it's measured by the spectrum of the galaxy here in the center. On the edge of this film are calibration lines. So these are emission lines from some known substance that is hot enough that is giving off emission lines. And here the galaxy is receding at 15,000 kilometers per second, and so forth. So they made a plot. This was a plot that Hubble made of galaxies showing there's a significant spread. Well, this is the early 1920s. But it seems to follow a straight line. And the slope of the straight line is the Hubble constant. And this is the velocity in kilometers per second. And this is the distance in parsecs. So that's another unit that is often used like light years. A parsec is 3.26 light years. And the unit comes from measuring parallax of nearby stars, where you look at the shift in the background, or you shift to the nearby star relative to the background at 6 months observation apart. So if you hold your finger up, close one eye, and then close the other eye, you see that your finger shifts relative to the background. That's because we have two eyes, and that's how we determine the sense, the depth of field. That's how we determine how far away things are, at least give us a sense of that. Nowadays, let me go back. This is out to 2 megaparsecs. So that's 2 times 3.26 is about 6.5 million light years away. That's pretty nearby. But again, this is the 1920s. Technology develops. 100 years. It's all 100 years. And now we've been able to see other objects that we know the luminosity of and determine them out. You see, this is a little bit further out, 400 megaparsecs. You know, the first dot on here is not even as low as 2. 2 is way down. This is 10 here. And this is telling us that the slope is more like 72. Now, Hubble measured the slope, but he got it wrong. And so the universe was expanding much faster. And it turns out that the universe was a lot younger than some of the objects within it. That was a problem. But now everything seems to fit together, but there's still an issue with what the slope is, because these types of measurements that give us about 72 with its uncertainty are disagreeing with the observations of the microwave background, which is telling us more like 69. And the error bars are so small that these numbers are a problem. And that will be resolved hopefully soon. So Hubble announced to the world in 1929 that the universe was expanding. Now, I tell you that the galaxies are moving away from us. That's not entirely true. It appears to be that way. And I like this balloon illustration because it's got these galaxies on here, but it also has a grid. And as you inflate the balloon, obviously these galaxies move away from each other. But they don't move relative to the grid. So to say they're moving away from us is not quite correct, but okay, that's how we more intuitively understand it. It's actually the space in between us and those galaxies that is expanding. So space-time is getting bigger. And that causes the wavelengths of some of these galaxies to stretch and also redshifted. And so the James Webb is taking a series of galaxies here and looking at the features coming from hydrogen, but these features are normally in the ultraviolet. This is the beginning of the Lyman, known as the Lyman break. And they measure the shift that has taken place relative to the laboratory measurements. And that redshift translates into a Z number. And this Z number is 13.2 here. And then down here, it's not quite as shifted. And this shift is 10.38. And so this is how they can measure redshifts of these galaxies. And these redshifts are getting to be very early within the universe. So you take a series of other galaxies here, and this is the first image, the SCHMACS 0723, and they took spectra of these four galaxies and find these emission features. And you see this is 11.3, and we're going to 13.1 billion years. So now you look at these shifts, and a shift to 12 is 13.4 billion years. That's how long light has taken to get to us. So you're looking at a galaxy that is less than 370 million years from the beginning. And this is baffling. How can galaxies form so fast? And this is weirdness that somehow galactic evolution we're not quite understanding. But now we can observe it. And that's what Webb is able to do for us. See, this is 13.1 billion light years away that took light to get to us. And it's a galaxy that had existed for 560 million years after the Big Bang. And this is a Z of 8.8. So basically, this is an astrophysical journal that came out showing galaxies at different times. And so we're going to be able to understand galactic evolution much, much better. All right, moving on. Now we talk about pretty pictures. And this is the Eagle Nebula in Serpens Calda. It's a star-forming region, a star hatchery, beautiful nebula that is about 7,000 light years away, toward the center of our Milky Way, in the lower southern region. And you can see the eagle here. Yeah, this is the body of the eagle, the head, the wings, and the feet. And you can see the difference between a visible spectrum here of Hubble and an infrared spectrum. And you can see so many stars in the background and actually through the nebula itself.
Figured out how to move the.
There's a question somewhere or no? Okay. This is a web image of Jupiter. It's showing some of the aurora that is in the North and South Pole. And this is normally the red eye. And it's here nice and bright because we're looking in the infrared. So a beautiful detail here. Saturn, the rings of Saturn, and 3 different moons, including Enceladus. Enceladus was studied further by Webb because what happens, most of these moons are oceans with a frozen skin over it. And in the ocean, the frozen part might be tens of kilometers thick, but there's an ocean below there. And the tidal forces due to the close presence of Saturn cause stresses in the surface and sometimes develop cracks. And then it starts spewing out plumes of water. Europa is a moon of Jupiter that's much closer. And NASA has missions to study Europa. And, you know, you can collect some of this water from a plume or actually study it. Or what would be more fascinating is to send a probe that would go down into the ocean below and look for bugs. You know, that might be 20 years or so from now. And by then, aboard the probe, there might be the ability to determine the genome of life forms that it might encounter. And that becomes interesting because I'm sure the kind of life that's out there is based on the same DNA that we are, life on Earth. But they would be able to tell if we have a common ancestor with that life or not. And suppose we do. And that tells us that maybe life started somewhere else and came to Earth from somewhere else. And that probably begins to blow your mind. Well, who knows? It's an interesting question. So here's again Saturn, and here's Enceladus, and there's a torus of water vapor because it's cracked and it's pluming at these cracks. And this is a blown up image that Webb has taken and then is analyzed the center portion of that plume and finds water. Well, no surprise. Water is abundant in any sort of star form that has formed. So water is extremely abundant. The question is, what else might there be? So here's an interesting image. Fomalhaut is a very bright star in our sky. It's only 25 light years away. It's low in the horizon in the south. But here what they have done is that Webb has blocked the center star because it's so bright. And it then is able to see the protoplanetary disk that forms naturally when a star forms. You see, you begin with a cloud of dust and gas, and there's always some sort of rotation to it. And as gravity compresses it, it spins faster. What happens if you have a water balloon and you start spinning it? Well, it turns into a pancake eventually, right? And that's precisely what happens naturally without any miracles taking place. And this protoplanetary disk is made up of disk and dust and gas. And gravity continues to work in different parts of this as things coalesce and planets form. And that's what we're seeing here, is a protoplanet being formed in this disk in a nearby star. This is really close, 25 light years. Well, here's another planet a little bit further away. This is 1,150 light years. The constellation of Phoenix, again, it's a southern sky. It's called WASP 96b. And these acronyms, they always mean something, but can't keep track of all of them. And this is, the size of this planet is about a Jupiter, a little over a Jupiter, but the planet is very hot. So this is not a habitable zone. But here you're seeing the light curve of the star as the planet goes in front of it, and you see it dip. And this dip kind of tells you how big the planet is, physical size. And this is one of the ways how they've been discovering planets recently. And so far, there's more than 5,000 stars out there that have planets that we've been able to discover. So the interesting thing that has never been done before is that as this planet goes in front of the star, well, you have the light of the star going through the atmosphere of the planet. And then you can look at the spectrum of the atmosphere and be able to tell what's in the atmosphere of this planet 1,000 light years away. And so Hubble has done that. And here is showing you the, the dots with the air bars are the measurements of the spectrum, and a model fit is showing you the atmosphere and containing water, giving you these bumps. So this is a clear example that this planet has water. Well, no surprise. Water is abundant everywhere. Here's another planet, another WASP, 39b. The other one was 96b. But this is showing a bump here of carbon dioxide. Well, that's getting interesting. Well, volcanoes produce carbon dioxide. It's not necessarily some intelligent life breathing oxygen, right? That's not a good sign of life. Well, here's another one. This is a more interesting one, an exoplanet K2-18b. It's 8.6 Earth masses. It's 120 light years away. So this is maybe a place to go visit. It'll take a very long time. You know, the Voyager spacecraft is traveling about 60,000 kilometers per hour. You know how long it would take to get to the nearest star, which is only 4.3 light years away? 80,000 years. So that's an issue that I don't know how we're going to solve. The sun is going to turn into a red giant in about 3 to 5 billion years. And it will get 100 times bigger than it is, which means that the Earth would orbit the sun inside of it. So life on Earth will not survive. So there's a motivation for us to go elsewhere. Well, not us. Don't lose any sleep over that one. But how are we going to do it? I don't know. Star Trek had the answer, but that's science fiction, I'm afraid. But okay, they took a spectrum of this planet and they found methane. Methane itself is interesting because methane would be the basis of a lot of carbon molecules, which could be to lead to amino acids and so forth. But the interesting thing is that they find dimethyl sulfide, and there are these signatures of dimethyl sulfide. And the interesting thing is that as far as we know, dimethyl sulfide here on Earth comes from life forms. There's always something missing, so I wouldn't necessarily guarantee that this is a sign of life on K2. Who knows? More evidence, more evidence. Here's a beautiful object. I need to worry about the time a little bit. This is the Crab Nebula in the constellation of Taurus. This is a supernova remnant that exploded in 1054 AD, a little over 1,200 years. And imagine back then, a bright star showing up in the sky. They could see it during the daytime. That's scary. So they got their pots and pans and got out there and started banging on them. And sure enough, that scared it away. About 2 weeks, it was gone. Well, a supernova remnant, supernova type 2, leaves behind a neutron star. And a neutron star is about the size of East Lansing, but it has a mass of a sun and a half, or maybe sometimes two. So it's quite dense. It's basically nuclear matter. So there's all kinds of very interesting physics that take place. And this is the area that I study. This neutron star is rotating 33 times a second. It produces a beam of radiation, it has a strong magnetic field. We happen to be in the line of sight of that beam. So these objects are called pulsars. They pulsate, the crab pulsates in the visible, in the radio, in infrared, in X-rays, and in gamma rays as well. And we have seen it do its dance in all of those. Here, what's interesting about the image is we've seen Hubble images of these, but this gray haze is really coming from what are called synchrotron emission. These are electrons accelerated by the magnetic field of the neutron star and radiating. And so this is very, very interesting as well. And this is a blown up image. You see some toroids out of the center, which one of these is a neutron star. You don't see it glowing in the infrared. You see it glowing in X-rays, soft X-rays, because the surface is about 1,000,000 Kelvin. And that radiation from the heat would be in soft X-rays. So we come to another interesting object, a globular cluster. And this is M92 in the constellation of Hercules. And you see a lot of blue stars, but a lot of yellow stars. And these clusters are the oldest structures in our galaxy. They're not in the disk of the galaxy, but they orbit the galaxy. They're out in the galactic halo. There's about 150 of these that are orbiting there. And they were seen early on, and their distribution in the sky told astronomers more or less where we were relative to the center. We see more globular clusters toward the center of the galaxy because we're about 2/3 out in a nice calm area. These formed first in the formation of the galaxy. This is a Hubble image. This is a Webb image. And the infrared, well, it's telling a different story, and it's a small patch of that. But basically, what astronomers can do is plot the absolute brightness, or brightness, either way, because all these stars are at the same place, as a function of its color. And what you would expect to see for a young cluster is the whole main sequence of stars, which would be some sort of an S-shaped structure in here. And stars in the lower right are low mass stars, and the mass increases of the star as you go to the upper left. And so the sun is about a solar mass, and it will live for about 10 billion years. So somewhere out here is where the sun would be, but it is already moved off. This turnoff point basically tells you the age, approximately, the age of the cluster. And this is more or less telling us somewhere between 12 and 16 billion years, which is very close to the beginning. Maybe 13.2 billion years or so. I don't know what. There's a lot of scatter to this. Okay. This is a Hubble Ultra Deep Field image. An exposure that was collected from 2009 to 2010 over about a 4-month period. So the exposure is something like 11.3 days, I believe. And they made a big deal about this image because this was the deepest image that Hubble has been able to see. And they found this reddish galaxy, which tells you it's old, and they measured the redshift, and they blow this image up, and this is the galaxy with its telephone number, in case you want to learn about it. And there's a blurb, so this is 2011. It says, these observations provide us with our best insights into the earlier primordial objects that have yet to be found and are now being found. Well, who's this guy, Richard Bowens? He's the first author of this paper that announced this. He graduated from Hope in '94. He's a physics major. I don't know if you may no longer remember these guys. So this ultra deep field is about a 15th of the size of the moon. It's about 2 arc minutes. A degree is 60 arc minutes. The moon is 30 arc minutes. 1 arc minute is 60 arc seconds, and so forth. So this is your grain of sand at arm's length, okay? So 2 by 2 arc minute field of view. And there is 10,000 galaxies in that image. This is the image itself. 10,000 exposure of 11.3 days. And these are galaxies. Yeah, there's a few stars in here. They have this diffraction pattern. You can see a star there. There's another one down here, and so forth. Most of these fuzzy things are galaxies, just like our own. And so I show this to my night sky class, and I ask them, how does this make you feel? And so we know the size of the patch of the sky. We know how many galaxies are observed by this image. So we can estimate how many galaxies there are in the observable universe. And, you know, that which we can see. And of course, there's so much more beyond our observable universe that we cannot see. How big that is, I don't know. And so this is a comparison of Hubble, ultra deep field, and the James Webb, the same field of view. Yeah, and here is a section blown up. This is Webb, and this is Hubble. And you see more or less the same galaxies. Maybe a few you don't see in one or the other. But this took 11.3 days exposure. This was less than a day, 0.8 days, 0.83 days. So that's pretty amazing. And this is, you know, not dedicating Webb to look for a couple of weeks. Imagine what we're going to find. Okay, so the 2x2 chunk of space of sky contains 10,000 galaxies. We need to convert this into what are called steradians, because in the entire sky, there's 4 pi steradians. So then I take the entire sky and divide by this little chunk and multiply that by 10,000 galaxies, and I get 3.7 times 10 to the 11th. Well, let's see, that's 370 billion galaxies in the observable universe. They more or less estimate, even though this is a conservative number for our Milky Way, that there's 300 billion stars in our Milky Way. And let's say our Milky Way represents common galaxies, although it isn't. We would multiply these two numbers together, and we would get approximately 1 with 23 zeros after it. It's a big number, yeah. Well, you know, there again, our Milky Way is one of 370 billion, 300 billion stars in the Milky Way. So we get 37,000 billion stars, yeah, if you want to do it that way. It's 10 to the 23. Now, one crazy scientist who had way too much free time on his hand, or her hand, decided to count all the sand grains in all the beaches of the earth. It was cleverly done, and there's an announcement. There is a web link. You just can look it up. I Googled this. And the number is 10 to the 19. The number is smaller by 10,000. The universe, there are more stars in the observable universe than there are sand grains on all the beaches of the earth. And let me ask you, we've all been on beaches. We probably walked on the beach barefoot. You remember at some point? And how many of us found this one sand grain and picked it up and said, "Ah, this is so special. I'm going to take it home and put it in some place so that I can admire it." And that sand grain is us. Isn't that what we're doing? So what is the story of the stars? It's a heavy one. It doesn't make us big, does it? But I think I better end here, because there might be some questions and this is going to get a little more crazy. So it would take another 10 minutes or so, and I think I'd rather try to deal with some of your questions here and from afar, or however we work this. But thank you for your attention. Questions?
Of that 37 billion stars,
It's on, just get a little
Oh.
closer.
how many of them are planets? They're not planets, right?
No, they're stars, and how many of them are going to have planets, we don't know. But you would expect that an isolated star will have planets around it, because it's natural the way that a star forms, that it's going to have a planetary disk and form planets. Even stars that form and most stars form as multiple stars. Our nearest star, Proxima Centauri, is part of a triple star system known as Alpha Centauri. And the one that is closest to us is Proxima, and it has a planet. And yet it's a multiple star system. So it's too early to tell. But I don't know. There's a number similar to this 10 to the 23, maybe 10 to the 19. I don't know. That's still a lot. And then, there could be some habitable planets and perhaps life similar to ours.
And the question I have, do I understand correctly that you said there was a lot of water in these stars?
Yeah.
The water we know?
Yes.
So then the question I have, what about the moon?
The moon has water.
It does have water, but
Yeah, they've discovered water in it. They've slammed spaceships into it. So the water is underneath. And then slamming something into the moon causes this spew of debris out. And then if the sun is behind it, they can tell that it's water. That has been done. We found water on Mars. It's underneath the surface as well. Certainly water in Enceladus, and a lot of these moons are frozen, as the Voyager images told us way back when, many years ago. So water is abundant, and you have comets coming from the Kuiper belts that is beyond Neptune. You have comets actually in the asteroid belt. And then you have comets about a light year away in what is called the Oort cloud. And these are all dirty snowballs that carry a lot of ice. And, our sun is not special. I'm sorry.
This question will reflect my ignorance of this, but you're looking for the edge of things. That is the 13.8 billion years away, yes, years away. But that edge is moving away from us, is it not? And so, will it be difficult to get to the edge?
Yes, I mean, the universe is expanding. And actually, it's accelerating in its expansion, so things are moving away faster and faster. At some point, the galaxies will fade and the universe will be left with our own galaxy. That's it. And we lose sight at the beginning. We lose sight of the cosmic microwave background because of the rapid expansion. It has taken light 13.2 and so forth billion years to get to us. That actually means that this object is a lot further away because they're both our galaxy and its galaxy were moving away when it emitted the light. So we can actually see objects at a distance of about 46 billion light years away. And the observable universe is about 96 billion light years in diameter. And of course, things are moving away and we're losing the ability to then see the beginning.
Can you speak to the controversy around James Webb and the redshift, that they found that they are younger than they expected them to be the further out they went, therefore causing a controversy over whether the Big Bang is correct or not?
The controversy that I know, I'm not sure if Webb has yet estimated the Hubble constant. It's possible, but I don't know. I haven't seen something that it's done. But Hubble has done that, and they have done it in various ways, looking at different techniques. And there's a discrepancy between those measurements and the cosmic microwave background. It's this 72 number and 69 number. But the uncertainties in the two are small enough that you would say these two numbers disagree. The Big Bang model is not at risk. In fact, I would not call it a theory. I would say the Big Bang is well established to the point of saying that it's a fact. What comes before all of that is speculative. But the fact that these two numbers are disagreeing is telling us something we don't understand. And I'm not a cosmologist, so I can't speculate what it might be, but I believe they will figure it out soon. And maybe Webb might have something to do with it.
I'm not sure how to ask this question. Do you see the role, or how do you see the role of a divine being in the evolution of the universe? I mean, is there a point where science ends and theology takes over? I mean, I just find this totally incomprehensible.
Well, I have spent 40 years at Hope College teaching now and then a course, senior seminar, dealing with issues in science and religion. for me, the two ideas were never separate. I know we separate them, but I don't believe that science can answer all of our issues. I mean, you have already the story that the stars are telling us. That doesn't give us a lot of meaning, a lot of purpose, or a lot of hope. So we're going to have to find that somewhere else. But it's part of our experience, it's part of our existence. And so I would say both are needed. Now, I just got through teaching this at Hope Church in a very different context, you know. And if you're interested, there is a link because they recorded it and I can provide that. But here, I know this group, it's not necessarily everyone is religious, but it does raise some very interesting questions.
Are there any other questions?
Just a basic question about the telescope itself. What is the control mechanism for pointing it at a different part of the sky?
Any telescope that you want to point somewhere in the sky, you have to control its motion. And typically the way this is done, I know Hubble is this way, so you start spinning a disk inside of the telescope in a given direction, so you're basically adding a component of angular momentum to it. And maybe at the beginning it has no angular momentum because it's now rotating, it's just going through its orbit. And then you want to point it somewhere, so you start spinning a disk and you will cause it to move in a given direction. So you have three of these in different axes, disks that spin in different axes, so that you can move it in 3 dimensions. And normally, Hubble, I know, had 6 of them because they do break down. And Hubble is in orbit around the Earth, so they were able to repair some of those. And it normally had 6 functioning, now it only has 3 functioning. So if one more goes, they believe they can still do science with Hubble, but then shortly after that, well, it's toast. You will have to deorbit it and bring it down.
Early on, you talked about, or you showed a spectrum for a galaxy in the Aquarius constellation. And as I understood it, the elements that were identified in the spectrum were somehow indicative of the distance of that object. Can you explain how that works?
Yes. The elements, if you're looking at them at rest, have a particular signature. So astronomers are able to identify what the elements are. It's complicated because even the sun has so many different elements in it. But if you look at the spectrum and it's shifted, that means it's moving relative to us. For instance, you look at the sun, and we're in the equator of the sun, and the sun is rotating. So some of the sun is approaching us, and the other part of the sun is moving away. So one is shifted toward the blue end, and one is shifted toward the red end. That's the red and blue shift. How much they're shifted depends on that speed. And so if you measure the speed of the galaxy because of the shift, and then you go and you use Hubble's law, you get the distance because you're measuring the velocity. The velocity also gives you this z value. And the velocity gives you the distance. It's model dependent once you're getting quite far out there, but it's pretty good.
It is 2:30. Peter said he would be happy to stay after if people had other questions. Is there one more question somebody'd like to ask before we thank Peter for what he's given us today?
Well, two more questions, okay.
When you
He's
were,
eager enough, he's
okay.
standing up, so.
when you were talking about the black hole, I was surprised you were identifying brightness as a quality. 'Cause
Yes.
That perplexed me. I can't remember. Yeah, why is the black hole as bright as 40 million suns? I always thought the black hole was dark and absorbed light.
It is if it's not doing anything, but if it's eating material, which we call accretion, as the material falls into the black hole event horizon to be lost forever and ever, it radiates. Yes, well, in part. There's also a jet that is formed when an accreting black hole, that there are two jets opposite it's along the axis of rotation. And this is a jet composed of a twisted magnetic field that then focuses a lot of the radiation in a beam. If this beam happens to point at us, then we see it being very bright. But it's the brightness of that beam that is being referred to as 40 billion suns. And of course, some of these black holes are very far away, like this is what quasars are, which they look like stars in the sky. But when astronomers started taking a spectrum of them, they were baffled. And measuring redshifts that were billions of light years away, they couldn't be stars. So these are quasi-stellar objects, or called quasars, that are the centers of galaxies that are beaming a jet in our direction. Magnetic twisting is causing the beam of radiation to be focused.
Yeah, one of your early slides, you showed this telescope taking off and going through the setting up of the mirrors and things like that. And it got to a point where it's in orbit, not orbiting the Earth, but orbiting something. And is that the final orbit, or at some point is the Webb telescope supposed to move again?
No, that is the final orbit. There is a particular spot behind the Earth and in front of the Earth, between the Earth and the sun, that is, and behind the Earth and the sun, that if you go at a certain velocity, you can stay there as you orbit the sun. And these are called Lagrangian points. And if we want to look at the sun constantly, we go to the Lagrangian point that's between the Earth and the sun. And we have a whole series of observatories that are looking at the sun. There's also places in the same orbit as the Earth ahead of it and behind it. And we have two observatories in those locations that are looking at the sun. And this is the stereo solar observatory that is basically giving us two images of the sun, but they kind of remain there. And there's the issue is, how congested can this place come? Maybe at some point they deorbit those. I'm not sure what they do. But there've been other satellites out there, and there's currently Gaia and Euclid that I know of that are out there from the European Space Agency. You might say that. That's a stable region where you can stay there and orbit the sun. Right, right. That's the reason for being behind the Earth. Because you want to avoid as much sun as you can. And then it has all these reflectors that dissipate the radiation that it is getting from the sun and the Earth. And there's a whole series. It's a fascinating observatory, and you should look for how many different movements they had to go through to get this guy set up. It's incredible.
Peter, thank you so much for
Yeah.
I think you did blow our minds. So,
Marshall,
did a really good job of expressing how big the universe is.